Hello everybody, welcome back to another discussion in dynamics. Today we will focus on kinetics of particles. We will continue kinetics of particles and the subtopic today is kinetics in curvilinear coordinates, and we will do two examples. Example number one, normal tangential coordinate system, so it will be kinetics in normal tangential coordinates, and example number two will be kinetics in polar coordinates. Before we jump into example one, please have a look at these equations. I just wanted to remind you how accelerations look like when expressed in a normal tangential coordinate system and polar coordinate system. Okay, we will use these expressions today. Okay. Without further ado, let's dive straight into our discussion. Here is problem number one. As usually, take a couple of seconds to read and understand the problem statement. Okay, so what do we have in here? First of all, we have our mass M, right? Our package of mass M. That package is placed in a cup, and that cup is constrained by an arm, yes, and that arm is pivoting. That arm has length L. And what else do we know? We know that since this is our trajectory, we know that our acceleration that is tangent to the trajectory is constant, okay? So this is AS and this is constant. Okay, so let's summarize. What do we know? Knowns. We know mass, we know length, we know G, and we know that AS is constant. Is there anything else we know? I believe that this is important information. Package starts at rest, so we know that our V0 is 0, right? This is all what we know. And what they ask us to find? They ask us to find AS such that package starts flying out when theta is 60 degrees, okay? And then in part B, they will ask us to find corresponding side load. I will define what side load is in a second. Okay, any questions about the problem statement? I don't see any hands in the air, so let's start our solution. I hope I'm not going to surprise you that I am going to follow my recipe, okay? I'm going to follow my solution steps. We are in kinetics of particles. I personally don't know any other recipe to solve these problems. This is the only recipe I know. Sorry. Anyway, first step, free body diagram, right? FBD. Let's draw it for arbitrary theta, okay? And theta is defined here. Yeah. For arbitrary theta, and then we'll also draw KD. Yeah. Let's draw it for arbitrary theta, and then we will just set up theta to 60. Okay. So we'll just draw a general case, and then we'll think what will happen. What happens when theta is 60 degrees. Okay. So in order to draw something here, yeah, I should actually only draw a rectangle here. Okay. Because actually on free body diagrams we draw only masses, only particles, yeah. However, I think that it's beneficial to maybe draw like how that pivoting arm looked like initially and how it looks like right now. Okay, so let's draw these two dashed lines. And I'm also going to copy this one. I'm going to paste it here. Okay, we are ready to draw our forces. And as usually, I am going to go for the easy ones, okay? So there is for sure mg. Are there any other forces acting on our system? What do you think? Oh, yeah, James?
There are two normal forces, one following the angle of the arm and then one over that.
Great, yeah. So I will call them N. Maybe here, actually. I will call them N1 and N2. N1 and N2, yeah. Great. And James knows that because he detected two contact points, yes, between the arm and our package, yes? So James said that there is this green contact point here and here. Okay? And that's why we replaced these two contact points with these reaction forces. Okay? I want to have a digression right now, guys, because in the past I was grader, and I usually grade kinetics. I like kinetics, yeah, as probably you can see, yeah. And I noticed that some of you, not everybody, but some of you, for some reason, writes here N3, like, yeah, because you think that there is a contact point also here. And maybe there is a contact point. However, we have like two contact points on one line, okay? Yeah. So just do not replace them with two reaction forces, okay? Just replace it with one. Okay? Even though there is definitely at least one contact point there, at least one, yes? Maybe there are two, but it doesn't mean that you should replace all of them with these normal forces, okay? Because basically you will introduce one extra unknown, and your equations of motion will be unsolvable. Yes, you will have, yeah. So basically, introducing N3 will be redundant in that case. Okay. When I was a student, it took me a couple of evenings to understand it. Okay. Nobody expects you to understand it right now. Take some time. Take a couple of evenings to understand it. Yeah, and you will be good. Yeah. Or review your static notes. I think they cover it on statics. Yes. Actually, I don't know. I don't know what they teach on statics. Yeah, but they should. At least in my opinion, they should cover that on statics. That was a digression. I'm sorry. Let's go back to our solution. Okay. So we are done with all the forces on our free body diagram. Okay. Now let's see what can we introduce on the kinetic diagram. So I believe that Professor Zinn told us that we should solve that problem in a normal tangential coordinate system. Okay. Let's follow his suggestion. Why not? Yeah. So we're gonna do NT. Okay, since this is our trajectory, I believe that UT will be pointing this way. Oops. And UN will be pointing this way. So if this is the case, this will be MAT, and this will be MAN. Okay, guys, I think I'm done with these KD and FBD. Maybe I will also introduce theta here. Okay. Okay. Next step, equations of motion. But before that, we have a question. Yes? The reference axis. What is reference axis? x and y are also pointing this. X is always horizontal, and j is always vertical. And I would attach them here because this point does not move. Yeah, if you look at the drawing, that point does not move. So I would actually attach our I and j here. Yes. And there was a question of Sophia or Olivia. Because normal? Because it has to point inside the curvature. Yeah. And ut has to follow velocity. YouTube channel, video on that. Subscribe, like, and comment. Okay. I will send you a link with the video. Okay. Okay, guys. Any other questions? Let's move forward. Equations of motion. So I'm going to write sum of forces in the t direction and n direction. What are the positive directions? This one and this one, yes? And I'm going to get rid of that I and j, okay? We don't need them here today. So what do we have in the t direction? Definitely we have n2. Oh, by the way, and n2 is that side load, yeah? N2 is what they asked us in part B. This is the side load. N2, and I think that there is also one component of mg acting in the t direction, right? Okay, I have these two components. And where is theta? Wait a second. So theta will be here probably. And if this is the case, theta will be here also. Okay, so that component will be, if I am not mistaken, I hope mg sine theta. Okay, great. And mg cosine theta, right? So this will be plus mg sine theta. And that's all. M-A-T. And now in this direction we have minus n1 plus mg cosine theta, M-A-N. Okay, guys, we're done with FBD, we're done with EOMs. Any questions? Okay, so now, since we are in curvilinear motion, I also have like one automatic. The next step for me is automatic. I just go for the expressions for accelerations from the previous board. Yeah. So if you don't mind, I will just copy this one. Here. Yeah. We are indeed in normal tangential coordinate system, right? Oops. So our acceleration components will have such expressions: dv, dt, and an will be equal to v squared over rho. Okay, they must obey these expressions, yes, because the trajectory enforces them to look like that. Okay, at least this is what you should learn from the previous chapter, kinematics. Okay, so these are general expressions for AT and AN, but we are solving one particular problem, yes? So let's maybe express them not in a general form. Let's express them in a form they have to look in this particular problem, okay? So AT, I believe, is AS, and this is constant, yes? They told us that tangential acceleration is constant. Do you remember problem statement? And also, I believe that in here, our rho is also constant. Our rho will be equal to L, yes? V squared over L. Okay, and now let's plug these two guys in here. So we will have something like that. So instead of AT, I'm going to plug AS, and instead of an, I will plug v squared over L. Okay. So these are our equations of motion for general theta, yes, for arbitrary theta. However, something funny happens for theta 60. When theta 60, our package starts flying out, yes, from the cup. How that will impact our equations? Anybody? Which one?
Bottom one.
Yeah, N1, yes. Yeah, this one will be 0. When theta is 60, N1 is equal to 0. Yes, because, look guys, N1 is this guy. And when package starts flying out, we will get rid of this point of contact. That point contact will no longer be there, yes? Yeah, our package will lose contact. Great, thank you, Jared. Yeah, okay, so I'm just gonna erase this one. Jaden, sorry, but second time today. Grace and Jared. Okay, this will be your. I know, and she's not Grace. They will be your nickname today. No, I'm kidding. I'm sorry. Yeah. Anyway, any questions? What happened? Do you know why I got rid of that N1? Yeah. Okay, guys. So I don't know. I already forgot what they asked us for. So this is where we are in the solution. I forgot what the question was. Let me scroll up the board and see what they are asking us for. This is the problem statement. Oops. Okay, so in part A, they ask us to find AS such that the package actually flies out when theta is 60. So I believe this is tricky, actually. I solved the problem yesterday, and it was tricky, okay? Can I show you my solution steps? Yeah? So in order to solve this part A, I went for this expression only, okay? So this will be g cosine theta, and this is equal to v squared L, okay? But this is specific v, okay? This is the v that is obtained at 60 degrees, okay? When theta is 60 degrees, okay? So this is 60 degrees. So you guys can see that our v at 60 degrees, okay, is actually equal to gl cosine 60 degrees square root. Okay, I think that I have nothing against plugging 60 instead of the theta here. We can do that. 60, 60. 60, 60. 60. Okay, so that would be 1/2 GL square root. Okay, so we know that this is our trajectory. We know that this velocity here is 1/2 GL 60. Sorry, 1/2 GL. We know that it starts from rest, yeah, so V0 is 0. And I believe that we know the length of that arc, yes, because theta is equal to 60 degrees. I also believe that they told us in a problem statement that our acceleration s is constant. It looks for me like something to integrate, yeah, because we have like boundary conditions, we have arc length. Yeah, I'm gonna integrate, guys. Yeah, so AS is equal to either dv dt or the other definition of acceleration. Question to you, do we know how much time it takes that arm to go from 0 to 60? Yes, I see John. Your name is John. John is shaking his head. No, we don't know how much time it takes, but we know the distance, right? That red distance, by the way. So I think that this is useless for us. Yeah, we should go for the other definition of acceleration. Yes, we should go for this definition, v dv ds. Great. So let's do it. We will have v dv, and this is equal to as ds. Okay, and let's integrate. What are the integration bounds? I believe that when s is 0, our velocity is 0, and when s is equal to L times 60 degrees, so L times pi over 3, yeah? When this is the arc length, our velocity is 1/2 GL square root. These are the integration bounds. So let's integrate. We'll have 1/2 V squared from 0 to 1/2 GL square root. And this is equal to, AS is constant, right? This is constant. So this will be AS times L times pi over 3. Great. So this will be 1/2 times 1/2 GL, and this is equal to AS L pi over 3. L's cancel out. We can continue here. So I believe that since they ask us to find AS, this is the answer. AS is equal to 3 divided by 4 pi G. Yeah, if you want to simplify that number, you can grab your calculator and obtain 0.239 G. Both answers are fine. Yeah. Okay, guys. I told you it will be tricky, yeah. But this is how you get it. How do you like it? Or maybe you don't like it. But we did it a couple of times already, yeah? Such integration along the path, yeah? I think that even in discussion number 1, we did something like that. Or 2, I don't know. Any questions? And I don't know, your name must be, I will tell you on Friday, okay? What's your question? Your Grace. Okay, I'm sorry, Grace. Yes, you can. Yeah. I just like doing that because it shows you how it just shows you that I distinguish motion over time and motion along the path. Yes, you can do it because it's on the cheat sheet. Yes? Yeah. Jack? Okay. Any other question? Okay, so that was part A, and I think that we should still have part B. So what they ask us to find? Corresponding side load. Okay, guys, so I believe that, so we ended up with 2 equations, yes? But right now we used only one of them, yes? So I think it's natural, it's logical to use the other one to solve this part. Okay, can I scroll up the board and grab the other equation? Let me tell you exactly what I'm talking about. Aha, here. So we ended up with these 2 equations. Yep. And in order to solve part A, we just went for this one, marked with blue arrow, yeah? So I'm just gonna steal this one, and I'm gonna solve part A, okay? I mean, I'm gonna do it anyway, so. So this is what we derived earlier, and we just found AS, by the way. We just found this value. And they ask us for N2. So N2 will be mg sine 60 degrees minus MAS. So basically, N2 will be equal to mg sine 60 degrees minus mg 3 4 pi. Okay, so you can actually end up with such expression. So you will end up with such expression. Mg square root of 3 over 2 minus 3 divided by 4 pi. If you wanna, you can leave it like that, but you can, if you wanna grab your calculator and simplify it, N2 will be approximately mg times 0.627, I believe. Yes. This is answer B. And now questions. I don't know, I don't feel like good energy coming from you. Am I making you confused? No? It's fine? Yeah. Sorry, yes, Olivia? Yeah. Oh, yeah, because I don't know M. Yeah, yeah, I don't know M. So just leave it like that, yeah. On the quiz, I will make sure that it's specified. Don't worry about it, yeah. And the G, you can plug it there 9.81 or 32.2. I just don't know what units you prefer, yeah. So, yeah. They didn't tell us M. If I scroll up the board, you can see that actually we solve it symbolically, yes? The value of M is not specified anywhere. And I would not worry about that. I would worry about understanding dynamics. This is just a detail, right? Okay, guys, one interesting thing. I like details of such problems. So look, N2, we ended up with N2 positive. Yeah, it's a positive value, yeah? So if I scroll up the board, it looks like my guess was correct. N2 should be pointing this way, yeah? And that means that if N2 points this way, this is the point of contact between package and the arm, this one. Yeah. What would happen if we ended up with N2 negative? That means that my guess was incorrect, yes? That means that N2 actually points the other way, yes? And then contact point between package and the arm is here, this black point. Do you see that? Yeah. I don't know. I just like such details. Yeah. Yes.
But didn't the equations of motion below that didn't establish like down and to the right as the possible? Like right below this free body diagram.
Yes.
So then the negative value. I don't know. I'm confused. I forgot what I was asking.
No worries. So basically, this is I solve problems in magnitudes. Okay, I solve these problems in magnitudes. I assumed that this is the direction of N2, and this is how I entered it in our equation. Do you see? This is how I entered it there. Yes. Yes. So now, if I ended up with positive value of N2, that means that my guess was correct. But if N2 is negative, that means I have to flip the vector. Yeah. Okay. It was a digression also, you don't have to understand it, yeah. I like going sometimes beyond the material, okay? Okay, guys, what's up? Example number 2? Let's do it. Let's do it. And you know what I'm gonna say right now, yes? As usually, please familiarize yourself with the problem statement before we start our solution. Yeah, if you were late, attendance list is here with me. You can approach me after the discussion. Okay, guys, so what do we have in here? We have our particle that has mass m, Yes, even though it's not specified here. Our particle has mass m. Our particle is constrained by this cable of length L. Our particle is released from this horizontal position with velocity v0. Yeah, and we move on Earth. We have g pointing downwards. Yeah. Oh, that m is specified here, actually. Here. I didn't see it. Interesting. Okay, let's see what we know. We know m, we know L, we know v0, we know g, and we know that the angle beta, okay? But beta is variable, so let's maybe leave it there. Okay, and what they ask us to find? They ask us to find, I believe, angular velocity as a function of beta, so omega as a function of beta, and tension in the cable as a function of beta. Okay, I hope I'm not gonna surprise you, but I'm gonna again follow my recipe. Okay, so first step is FBD. Let's draw it for arbitrary beta, okay? For arbitrary beta. And this is kinetic diagram. Okay, so again in here I should only draw circle, okay? Because that circle has mass only. However, I'm just gonna draw two auxiliary lines, okay? So this is cable in the initial position and cable in the current position. And this is our beta, by the way. This is our beta. Okay. So what forces act in our system? mg is reserved for me. And is there any other force? Yeah, tension in the cable, yes. Tension in the cable, pointing this way. Okay, there are no other forces acting on our system. Now, kinetic diagram. And again, Professor Zinn told us to solve that problem in polar coordinate system, so r theta. And we are going to follow his suggestion. Why not? So let me introduce this polar coordinate system here. So since this is our, so I would specify origin here. Yes, so if I specify origin here, this is our position vector, right? R. So in that case, our UR will be aligned with R. And theta has no other choice. Theta has to be on the left-hand side of UR. Theta will be pointing this way. And now this is the first point I had to stop yesterday, yeah, while solving that problem to myself. Because I have to introduce that angle theta that specifies the orientation of our coordinate system. And there are three requirements for the theta. Theta has to be oriented this way. Yeah, it has to be counterclockwise, yes? It has to start from horizontal line and it has to end up at UR. So I hope that if we, in order to satisfy these three requirements, our theta will look like that. This is our angle theta. Okay, guys, we'll get to that in a second, okay? Now let me introduce our inertia forces. So MAR has to be aligned with UR, and MA theta has to be aligned with U theta. All right. We are done with our FBD and KD. So now equations of motion. Sum of forces in the R direction and sum of forces in the theta direction. Positive, positive. So what happens in the R direction? We have minus T. And I think I should project mg on this direction and this direction. So if beta is here, beta will be here, and beta will be here. So this one will be mg sine beta, and this one will be mg cosine beta. Okay, so in here I will have plus mg sine beta. And this is equal to MAR. And this one will be minus mg cosine beta, and this is equal to MA theta. All right. What do you think of that? All the forces, I mean, FBD looks good for you, and equations of motion look good for you. So now I have that automatic step again. Since we operate in polar coordinate system, I'm going to switch the board, and I'm going to steal these equations from the other board, okay? Because this time we're going to use these ones to express our accelerations. Okay, so our AT is equal to r double dot minus r theta dot square, and our AN, oh, what I'm talking about, AR and A theta, sorry guys, theta plus r. Okay, and I would like to plug these expressions here again, right? However, they are still expressed in a general form. Let's simplify them, yes? Let's use some information from our problem statement to simplify these expressions. First of all, do you think that r is constant? Yeah, r is constant. Plus it's equal to L. Yeah, so I'm not gonna even ask you what is r dot and r double dot, because you all know that. They will be 0 and 0. Great. Second modification is following. Do you guys see that our, if I scrub the board, that our, and if you look, that if you look here actually, yeah, okay, do you guys see that our beta plus theta is 360? Do you see that? Yeah, so I can actually express theta as some constant value minus beta. Okay, and now if I differentiate twice, I mean once and then one more time, I will end up with such expressions. Theta dot is equal to minus beta dot, and theta double dot is equal to minus beta double dot. I would like to plug information from the green box and black box in here. Okay, and I will end up with such expressions. First of all, I can get rid of this expression and this expression. So I can actually erase it. And then I believe that the first one will be L beta squared with negative value, and this will be minus L beta double dot. Okay, so now let's plug these values there. I mean these values here. Okay, so what we will have here? We'll have these two expressions. Oops. Okay, guys, how does that look like from your perspective? We have FBD, we have EOMs, and we plug in these fancy expressions for accelerations. So far, so good? Okay, and again, I forgot what the question was. I must copy it from the top of the board. So this is what they ask us for. Aha. They ask us to find omega, yes? So angular velocity, and they ask us to express it as a function of beta. Not good, because I don't see omega anywhere in here. Yeah, we must bring omega to these equations, yes? Any idea how to do that? For example, this is beta, right? Yeah, and if I take first time derivative of beta, what is first time derivative of beta? It is omega. Yes, it is omega, yes? Okay, guys, so we basically have that beta dot is omega, yes, and beta double dot will be d omega dt. Okay, so I will just plug these values here. Okay, so I'm gonna copy paste again, thanks to technology. Yes, and I'm sorry to those of you who use pen and paper. So this will be omega, and this will be d omega dt. Whew. That's a long problem, huh? Don't you think? But I hope I am not confusing you, at least too much. Okay, guys, they ask us to find omega. They asked us to express omega as a function of beta. I solved it yesterday. It can be obtained if we look at the second equation. Okay, let us look at the second equation and we'll solve that problem. Okay, so check this out. First of all, in here, we can actually simplify it, right? Because I think that minus cancels out and these m's cancel out. Yeah, so I can actually write g cosine beta, and this is equal to L d omega dt. Okay, and now I would like to have conversation with you that is similar to the one I already had with you in this discussion. Please look at the right hand side. In here we have d over dt. That means that eventually we will integrate over time. Yes? The question to you, do you see any explicit function of time in the left hand side? No. But the variable there is beta. Do you see that variable in the left hand side is beta? Beta changes in time. Yes, indeed. You can see it here. Yeah. But we do not know expression for beta. Yeah. That's why we must switch the variable. We're gonna do this little trick you already know. D omega dt is equal to d omega dt, and I'm just going to divide it by d beta and multiply it by d beta. Okay? And you guys can see that this expression all of a sudden is beta dot, right? And this is omega. So this will be omega d beta. Oof. So actually we will solve something like that. Cosine beta is equal to L omega d beta. And now our variables are consistent, right? We have beta on the left hand side and we will integrate over beta as well. So let's do it. We will have L omega d omega, and in here we'll have g cosine beta d beta integral. Okay, so I believe that what are the integration bounds for beta? I believe that our beta starts from 0 and ends at some beta. So I will put 0 here and beta here. And now what are the bounds for omega? Wow, we still don't know it, yeah? But we know that if you look at the right side of the corner of the screen, we have V0 in here, yes? So I believe that V0 will be equal to omega 0 L, right? So our initial omega will be actually V0 divided by L. So I can put V0 divided by L, and we will end up with some omega. I don't know. We will see later. Some omega at some angle beta. So now let's integrate. This will be L 1/2 omega squared in integration bounds from V0 L to omega. And if I remember correctly from school, integral of cosine is sine, yes? So it will be G sine beta from 0 to beta. Okay. So let's plug this in the integration bounds. And we will end up with L 1/2 omega squared minus L 1/2 V0 squared L squared. And this is equal to G sine beta. Okay, so we are almost there because they ask us to find omega, right? So our omega squared will be equal to 2G divided by L sine beta plus V0 squared L squared, right? But they ask us to find omega, not omega squared. So our omega will be equal to exactly the same, but under the square root. So this, but just put it under the square root. Let me double check if this is what I obtained yesterday. Yes, this is what I obtained yesterday. Okay, so this is answer to part A. Yeah. That was a long part A, don't you think? Anyway, it's already 11:50, so let me just summarize what we did today, okay? And I will finish part B after our discussion, and I will post it on YouTube, okay? Hello, everyone. In our discussion, we didn't have time to finish part B of example number 2. That's why I decided to finish it after our discussion. Here is the solution. They ask us to express tension in the rope as a function of beta. And in part A, we used only one of the equations we derived, right? So I think that it's natural to use the other one in part B. Let me scrub the board and show you what I'm talking about. So I believe that in part A, we use this equation. And now in part B, I think we should go for this equation, and we will solve the problem. So let me copy it from here. I can copy it here. And I think that some of you already see that that problem would not take much, yeah, because basically our tension can be expressed as mg sine beta plus ml omega squared, where omega squared was found in part A here. So let me just plug that value in here. We will have T is equal to mg sine beta plus ml 2 GL sine beta plus v0 squared L squared. And if you simplify this expression, you should end up with following expression: 3mg sine beta plus m v0 squared L, v0 squared divided by L. And this is exactly what we were fishing for. This is answer part B, since this is exactly tension expressed as a function of beta. Okay, so thank you for today. I hope everything was clear during the discussion. In case you have questions, feel free to stop by our office hours, post them on Piazza, or you can also leave some questions in the comment section below this video. Thank you and see you next time. Bye.